This is Physics 2212, Lab 3. In this lab report, I will first introduce the experiment and then explain the computational model and code. I will then follow with the results, discussion, and the conclusion. The purpose of this lab is to measure the distance dependence of a small bar magnet and compare the empirical measurements to the predicted measurements from the equations of the on and off axis magnetic fields derived from the Biot-Savart law. This will be done using a GlowScript program to calculate the simulated magnetic field of a magnetic dipole. The fundamental principles of this lab include the Biot-Savart law, the magnetic dipole moment, and the magnetic field of the dipole. Equations for all of these are presented on the slide, but the most important ones will be the on-axis parallel magnetic dipole equation and the Kr raised to n equation and the linearization of magnetic data. The general form of the magnetic field of a dipole will be used in the GlowScript computational model. A key principle is that of superposition. The total magnetic field is the sum of the individual magnetic fields at the observation location. A preview of the results is that the magnetic dipole moment is 10.3 am squared, the experimental 45-degree magnetic field magnitude is 3.67 times 10 to the negative 5 Tesla, and the predicted magnitude is 6.65 times 10 to the negative 5 Tesla. For the experimental aspect, the system is the magnetometer chip in the phone. The surroundings are the bar magnet, the earth, and everything else. The key assumptions of this lab are that there is negligible interference from the surroundings and the magnetometer readings, and that the Earth's magnetic field is properly compensated for and there is no error by moving the phone slightly. For the overview of the procedure, first, compensate for the Earth's magnetic field. Second, find the location of the magnetometer chip on your phone and use a magnetometer app to measure the on-axis and off-axis magnetic field of a small bar magnet at differing locations and a 45-degree angle. Lastly, complete multiple trials to calculate an average value of the magnetic field. As for the observations, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This is seen in the experimental data as the magnetic field decreases with increasing distance. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here is the experimental and data processing. From experimental data, the linear regression is y is equal to negative 1.9872x minus 13.094. Thus, ln k is equal to negative 13.094 and n is equal to negative 1.9872. By equating the two equations for the magnetic field of a magnetic dipole shown in the introduction, we can calculate the value for mu, which we found as 10.3 am squared. For the computational model, the initial conditions and constants include mu0 over 4 pi, which has a value of 10 to the negative 7, and mu mag, which was 10.3 and calculated in the previous slide. The full code is available in the description of this video. Figure 1 shows the definition of a function to return the magnetic field given certain data. Figure 2 is 4 out of 6 arrows that show the direction of the magnetic field. And figure 3 is the formula in code to calculate the magnetic field at a 45-degree angle using the general formula for the magnetic field of a magnetic dipole. Here are the results of the Python model. The magnitude of the simulated magnetic field at 45 degrees is given in the second last line as 6.65 times 10 to the negative 5 Tesla. The experimental value found in the spreadsheet was 3.67 times 10 to the negative 5 Tesla. It seems that the model overpredicts the magnetic field, but they are still the same order of magnitude, so we are still somewhat accurate. It was most likely experimental error that led to this disparity between the values. The possible sources of error in this experiment include interference from other magnetic fields, for example, electric devices, which is related to the superposition principle, moving the phone slightly or slight shifts in angle causing interference from the Earth's B field, inconsistency in measuring the distance between the magnetometer and the magnet, and fluctuating measurements from the magnetometer. Lastly, for the results, discussion, and conclusion, the magnetic dipole moment was 10.3 am squared, the experimental magnitude was 3.67 times 10 to the negative 5 Tesla, and the predicted magnitude was 6.65 times 10 to the negative 5 Tesla. For the additional questions, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid it out at some intermediate angle? Both the x and y components of the measured magnetic field would be affected by the Earth's magnetic field. The x and y components specifically would change simultaneously at an intermediate angle, but the Z component would not change that much because the magnetometer was kept at a flat surface and not moved up or down. What if you were to stick two identical magnets together end to end and run the experiment again? The B field magnitude would likely increase by approximately double, as the two magnets would combine their magnetic fields in accordance to the principle of superposition. The distances measured in the experiment would also decrease due to an increased magnetic field. Thank you.